Here's something that should bother you. People talk about quantum mechanics like it's this impossibly complicated thing. Like the rules go on for pages, like you'd need years of higher mathematics just to understand what the rules are. And that's not true. It's just not. Quantum mechanics has a very small number of rules. I mean, small. You could write them on the back of an envelope and still have room for a grocery list. 6 rules. Maybe 5, depending on how you count. That's it. That's the whole game. Now, here's the part nobody tells you. The rules aren't hard. The rules are strange. They're not complicated the way tax law is complicated, where there are 1,000 exceptions and subclauses. They're simple the way a poem is simple. Every word carries weight, and some of those words tell you things about reality that your brain is going to fight. Because here's the crack in the whole thing. Every one of these rules has been tested. Tested to a precision that makes your bathroom scale look like a wild guess. And every one of them says something about the world that flatly contradicts what you experience every single day of your life. So let me walk you through them. Not the math, the ideas. What does each rule actually say? And why should it keep you up at night? Let's start with the first rule, because it's the one that got the whole thing started, and it's the one most people skip right past. Energy comes in chunks, not smoothly, not in a continuous flow like water from a faucet, in lumps, discrete packets, little indivisible portions that Max Planck in the year 1900 called quanta, which is just the Latin word for how much. Now, I want you to try something. Hold your hand up in front of you. Move it slowly from left to right, smooth, right? Continuous motion, every position along the way, no jumps, no gaps. That's how you think the world works. That's how Newton thought the world works. And for your hand, at the scale of your hand, it basically does. But now imagine you could zoom in, way in, past the skin, past the cells, past the atoms, down to where electrons are doing their thing around a nucleus. And at that level, something very different is happening. And if the electron doesn't get to have any energy at once, it gets specific amounts, specific levels, and nothing in between. That's not a metaphor. That's not me being poetic. An electron in a hydrogen atom can have this much energy or that much energy. And there is literally no state that corresponds to anything in between. It's as if you were climbing a staircase, except the stairs are the only thing that exists. There's no ramp, no slope, no between the steps. You're on one step or another, period. This was the first crack, and it showed up in a very specific experiment that I think deserves your attention. In 1922, 2 German physicists, Otto Stern and Walter Gerlach, did something beautifully simple. They took a beam of silver atoms and sent them through a magnetic field, not a uniform field, one that was stronger on one side than the other. Now, classically, what should happen? The atoms have angular momentum. They're spinning like little tops, and they should be spinning at all different angles, randomly. So when they pass through this non-uniform field, they should fan out into a smooth blob on the detector, a continuous smear. That's not what happened. The beam split into 2 distinct spots, just 2, not a smear, not a spread, 2 clean dots, as if the atoms could only spin in exactly 2 directions, up or down, and nothing else was allowed. That's quantization. That's rule 1 in action. And notice what it's telling you. It's not just saying energy comes in lumps, it's saying angular momentum comes in lumps. The very act of spinning, something you think of as smooth and continuous, turns out to be digital at the fundamental level, discrete, clicks, not sweeps. And that should bother you, because it means the universe, at its root, is not the smooth, continuous thing you feel it to be. But that's not the strange part. That's just the first rule. The second rule is the one that made even the physicists uncomfortable, and I mean uncomfortable. Not confused, not puzzled, but genuinely unsettled. Here it is. The quantum system doesn't have to be in one state. It can be in a combination of states all at once, not we don't know which one. That's different. That's just ignorant. It's in multiple states simultaneously. And each state in the combination has a weight. Now I know how that sounds. It sounds like mystical nonsense. It sounds like something someone says at a dinner party after too much wine. But I'm going to show you exactly what it means. And I'm going to show you with the experiment that I think contained. I really believe this. The only mystery of quantum mechanics, the double slit experiment. Picture this. You've got a wall with 2 narrow slits in it side by side. Behind the wall there's a detector screen, a surface that records where things hit. Now you take a source that fires tiny particles with, let's say, electron, one at a time, one electron, then another, then another. Each one goes through the wall and hits the screen somewhere, leaving a little dot. You fire 1,000 electrons, 10,000, you wait, and you look at the pattern on the screen. Now, if electrons were just little bullets, little tiny balls flying through space, you'd expect two clusters of dots, one behind each slit, like throwing pebbles through two windows. Simple. That's not what you see. You see a pattern of stripes, bright bands and dark bands alternating across the screen, an interference pattern, the exact pattern you'd get if you were sending waves through those slits. Waves that overlap, reinforce in some places, cancel in others. But here's the thing that should really get to you. You're sending the electrons one at a time. One single electron alone and by itself goes through the wall and hits the screen. There's no other electron to interfere with. And yet over time, the pattern that builds up is an interference pattern. The electron interferes with itself. And the only way the mathematics can account for this, the only way, is if the electron in some sense goes through both slits simultaneously, not one or the other. Both. It exists in a superposition of went through the left slit and went through the right slit. And those two possibilities interfere with each other to produce the pattern you see. You're thinking, fine, so let me just watch. Let me put a detector at the slits to see which one it actually goes through. You can do that. And the moment you do, the interference pattern disappears. You get two clumps, just like little bullets. And the act of determining which slit, the act of knowing, destroys the superposition. That's rule 2. A quantum system exists in a superposition of states, and it stays that way until something interacts with it in a way that distinguishes those states. The electron doesn't go through one slit. It doesn't go through both slits in any classical sense. The question, which slit did it go through, doesn't have an answer until you force it to have one. And forcing it changes the outcome. If that doesn't unsettle you a little, you haven't understood it yet. But this isn't even the deepest rule. That comes next. Now we get to the rule that I think is the heart of the whole thing. The rule that makes quantum mechanics quantum mechanic, and not just classical mechanics with some weird restriction. And it's this. You don't calculate with probabilities. You calculate with amplitudes. See, in everyday life, probability works the way you'd expect. If there are two ways something can happen, and one has a 30% chance and the other has a 20% chance, the total chance is 50%. You add them up. Done. That's how betting works. That's how insurance works. That's how your brain naturally thinks about chance. In quantum mechanics, that's wrong. Instead of probabilities, each possible way something can happen is assigned a number, a probability amplitude. And this number isn't just a regular number. It's what mathematicians call a complex number. It has a magnitude and a phase. Think of it like a little arrow with a length and a direction. To find the probability of something happening, you don't just add up the chances for each path. You add up the amplitude, these little arrows, and then you take the square of the result. And here's why that matters. Arrows can point in different directions. When you add two arrows pointing the same way, you get a bigger arrow, higher probability. But when they point in opposite directions, they cancel each other out. You get a smaller arrow, maybe 0. That's where the interference comes from in the double-slit experiment. The electron going through the left slit has an amplitude. The electron going through the right slit has an amplitude. At certain points on the screen, those two amplitudes point in the same direction. They add up, the probability is high, you get a bright band. At other points, they point in opposite direction. They cancel, the probability is low or 0, you get a dark band. If you were just adding probabilities, which are always positive numbers, you'd never get cancellation. You can't add two positive numbers and get 0. But amplitudes can cancel. That's the whole trick. That's the entire engine of quantum mechanics. Let me give you something to make this vivid. Imagine you're in a room with two doors. Behind each door is a hallway that leads to the same exit in a normal world, a classical world. If I block one door, fewer people get to the exit. Obviously, blocking a path can only reduce the flow. But in a quantum world, something astonishing can happen. There are situations where blocking one of the paths actually increases the probability of arriving at the exit. Because with both paths open, the amplitudes for the two paths were canceling each other out. Block one, and the cancellation goes away. and the surviving amplitude is now unopposed. More particles get through. You want to say that's impossible, that blocking a route can't help you get somewhere. And in your daily experience, you're right. But at the quantum level, it happens. It's been measured. It's real. This rule, the shift from probabilities to amplitude, is the single most important idea in all of quantum mechanics. Everything else follows from it. Interference, entanglement, the uncertainty principle. They're all consequences of the fact that the world runs on amplitudes, not on odds, and nobody knows why. That's just what it does. But here's the thing that keeps the mystery alive. The fourth rule is the one everybody's heard of and almost nobody understands correctly. The Heisenberg uncertainty principle. Now, here's how most people think of it. You can't measure a particle without disturbing it. You try to see where an electron is, you have to bounce light off it. And that light kicks the electron, changes its momentum. So you've messed it up. Measurement is clumsy, end of story. That's not what the uncertainty principle says. That picture, the observer disturbing things picture, was actually an early attempt by Heisenberg himself to give an intuitive explanation, and it's misleading. It makes the uncertainty principle sound like a practical limitation, like if we just had better instruments, more delicate tools, we'd get around it. You can't get around it. It's not about instruments, it's about what exists. Here's what the rule actually says. There are pairs of properties, position and momentum, energy and time, where the act of making one of them precise necessarily makes the other one imprecise. And this isn't because of some clumsiness on our part, it's because a particle that has a perfectly definite position simply does not have a definite momentum. The momentum isn't hidden, it isn't there to be found. The particle genuinely doesn't have one. Let me show you why this follows naturally from Rule 3. From the amplitude idea, picture a wave, a pure, perfect wave, a single frequency, extending forever in both directions. That wave has a beautifully precise wavelength, and in quantum mechanics, wavelength is directly related to momentum. So that wave represents a particle with a perfectly definite momentum. But where is the particle? The wave extends everywhere. It's not localized. It's equally likely to be found anywhere along the entire wave. The position is completely undefined. Now picture the opposite. Take a bunch of waves with different wavelengths and add them together just right so that they reinforce in one tiny spot and cancel everywhere else, and you get a sharp spike, a wave packet. Now the particle has a pretty definite position. It's concentrated right there at the spike. But what happened to the wavelength? You used a mix of wavelengths to build that spike. The momentum is now a mix of values that's spread out, imprecise. That's the trade-off. And it's not a trade-off in our knowledge, it's a trade-off in reality. The particle can't have both a definite position and a definite momentum, for the same reason that a musical note can't be both perfectly sharp in pitch and perfectly brief in time. And a short click has no definite frequency. A pure tone goes on forever. It's built into the mathematics of waves themselves. That's the uncertainty principle. Not measurement is hard, not we're too clumsy. It's the universe doesn't contain the information you're asking for. You're asking a question that doesn't have an answer. And yet, and this is the part that I think is beautiful, the universe gives you exactly as much precision as it can. The uncertainty principle tells you the minimum uncertainty. It's not chaos. It's a precise rule about imprecision, a law governing the limits of knowability. You're thinking, this must only matter for tiny things, electrons and photons. And for the most part, you're right. The uncertainty is so fantastically small for everyday objects that you'd never notice. The quantum fuzziness in the position of a baseball is so tiny that it would take longer than the age of the universe for it to drift off course by the width of a single atom. But the principle is universal. It applies to the baseball too. It applies to you. It applies to everything that exists. The universe is not even in principle fully knowable in the way Newton imagined. And that's Rule 4. Now let me show you what happens when you put these rules together. All right, this is the rule that causes the most arguments. More ink has been spilled on this one than the other 4 combined, and I'm going to tell you exactly what we know, what we don't know, and where I think people go wrong. Rule 5. When you measure a quantum system, you get a definite result, and the system changes to match. Here's what I mean. And before you measured, the electron is in a superposition, combination of states with an amplitude for each possibility. When you measure, you get one result, just one, and after the measurement, the electron is no longer in that superposition. It's in the state corresponding to the result you got. The amplitudes tell you the probability of each outcome. If the amplitude for spin up is large and the amplitude for spin down is small, you're more likely to measure spin up. But which one you actually get on any single measurement? That's random. Genuinely, fundamentally, irreducibly random. And not random because we don't know enough, random in a way that nothing in classical physics is ever random. Einstein hated this. God does not play dice, he said, and I understood his objection. It's a reasonable objection. In every other area of physics, randomness is just a word for ignorance. If you flip a coin, it's random to you because you don't know all the details, the exact force of the flip, the air currents, the surface texture. But in principle, if you knew everything, you could predict it. Determinism underneath. Quantum mechanics says no. The randomness is not a cover for deeper determinism. It's the bottom floor. There's nothing underneath. Now, here's where people go wrong, and I want to address this directly because I know you're thinking it. You're thinking. Measurement means consciousness. A human mind has to look. The observer has to be aware. Consciousness collapses the wave function. And maybe, just maybe, this means the mind has some special role in physics, some privileged position in the architecture of reality. And you're not wrong to think that, and it's a seductive idea. Some very smart people have entertained it. Eugene Wigner, a Nobel laureate, took it seriously for a while, but here's where it breaks down. Every experiment we've ever done is perfectly consistent with measurement. Being any physical interaction that records information, any interaction that correlates the state of the quantum system with the state of something in the environment. It doesn't have to be a human mind. It doesn't have to be a conscious observer, a photon bouncing off an electron and flying away into the room. That's a measurement. A stray air molecule interacting with a particle, that's a measurement. The environment is measuring things all the time, trillions of times per second, without a single conscious observer anywhere in the picture. This process, the environment constantly interacting with quantum systems and washing out their superpositions, has a name, decoherence, and it explains why you never see quantum superpositions in daily life. It's not that your mind is special, it's that you're big. You're made of trillions upon trillions of particles, all interacting with the air, with light, with the floor, with the chair, and every one of those interactions is a kind of measurement. Superpositions at your scale get destroyed almost instantly, far too fast for you to ever notice them. And I want to be honest with you here, decoherence doesn't completely solve the measurement problem. It explains why you don't see superposition, but it doesn't fully explain why you get one specific result. It tells you the menu, but it doesn't explain why the universe picks a particular dish, that question. What actually happens at the moment of measurement, why this outcome instead of that one, is as of right now genuinely unresolved. There are interpretations. Many worlds says every result happens, and the universe branches. Copenhagen says don't ask questions that experiments can't answer, just calculate and move on. Pilot wave theory says there is a hidden determinism after all, with a guiding wave nudging particles along definite paths, and we just haven't found it in the standard formalism. I'm not going to tell you which one is right, because nobody knows, and anyone who tells you they do is selling something other than physics. This is the open frontier, not the rules, which we understand very well, but what the rules mean. What kind of reality are they describing? That's rule 5, and it's as honest as I can be about it. Now, let me tell you about the one that Einstein called spooky. Here's the last rule, and in some ways it's the most unsettling of all, because it's the one that tells you the universe isn't made of independent parts. Entanglement. Here's the idea. Take 2 particles. 2 electrons, 2 photons, doesn't matter. Let them interact in a way that links their quantum states, then separate them, pull them apart. Send one to London and one to Tokyo. Now measure a property of the one in London. Say its spin. The moment you get your result, you instantly know the spin of the one in Tokyo without measuring it, without anyone in Tokyo touching it, without any signal passing between them. You're thinking, so what? Maybe they were just correlated from the start, like a pair of gloves. I put one in each box, ship them to different cities. You open yours in London, find a left glove. You know mine in Tokyo is a right glove. Nothing spooky about that. And you're right, that isn't spooky. And if that were all entanglement was, Einstein would have been satisfied. He proposed exactly this picture in 1935, along with Boris Podolsky and Nathan Rosen. The famous EPR paper, it argued that quantum mechanics must be incomplete, that there must be hidden variables, properties the particles carry with them from the beginning. that predetermine the outcome. It's a reasonable, intuitive, thoroughly classical idea, and it's wrong. In 1964, the physicist John Bell proved something extraordinary. He derived an inequality, a mathematical constraint on correlation, that must be satisfied if the particles are carrying hidden variables. If the glove picture is right, if the outcomes are determined in advance, and then certain combinations of measurements on the two particles can only be correlated up to a specific amount. There's a ceiling, a hard limit. And quantum mechanics predicts that this limit can be exceeded. So who's right? In 1982, Alain Aspect and his team at the University of Paris did the experiment. They created pairs of entangled photons, sent them in opposite directions, measured their polarizations at different angles, and checked whether the correlations violated Bell's inequality. They did, decisively. The correlations were stronger than any hidden variable theory could produce. The particles were not carrying predetermined answers. The outcomes were not decided at the moment of separation. Something happens at the moment of measurement that connects the two particles in a way that has no classical explanation whatsoever. Let me give you a thought experiment to feel the weight of this. Imagine two coins, quantum entangled coins. I give one to you and one to a friend. You travel to opposite sides of the galaxy, 100,000 light years apart. You each flip your coin. In a normal world, your results would be independent. Sometimes both heads, sometimes one of each, sometimes both tails, randomly with no special correlations beyond what you'd expect from chance. But with entangled coins, you find something that shouldn't be possible. Your results are correlated in a way that no prearranged scheme could reproduce. Not if the coins were programmed before separation, not if they carried hidden instructions, not if they consulted shared lists. The correlations are stronger than any local, predetermined mechanism can produce. It's as if the coins were communicating instantly across 100,000 light years, except they're not communicating. Here's the thing that saves physics from complete insanity. You can't use entanglement to send a message. The results on each side, taken alone, look completely random, and it's only when you compare the two sets of results, which requires a classical signal limited by the speed of light, that you see the impossible